Hello everyone. Thank you for joining us. Today we are going to talk about electromagnetic clutches. One of the many design challenges of an electromagnetic clutch is to predict the holding force. Through today's webinar, we will see how EMS for SOLIDWORKS can be used to address such challenges. Today from EMWorks team, Arvind Krishnan and myself, Kal Dasaroju, will be presenting this webinar. Before discussing our today's agenda, let me introduce us. My name is Kal and I'm working as an account manager for EMWorks. I handle commercial sales and marketing activities for our company. My colleague Arvind works as a director of product management. He is an expert user of EMS software and has extensive knowledge in low frequency electromagnetics. Feel free to write down our details to email us afterwards for any inquiries. You can also connect with us over LinkedIn. Moving on to the agenda of today's presentation, I will be briefly discussing about our company EMWorks, where we are located, the products we offer. Then my colleague will present the technical part of today's webinar. At the end of this technical presentation, I will talk about various learning resources offered by EMWorks for its users. EMWorks offers 3D and 2D electromagnetic simulation software as an add-in tool for SolidWorks and Autodesk Inventor 3D CAD. Our company was founded in the year 2000. We have a vast sales network in the form of 2 offices and a global reseller channel. We provide our solutions and services directly or through a reseller in America, Europe, and Asia Pacific region. Our company has a strong research and development team with years of experience in the field of electromagnetics. Our products are gold certified by Dassault Systems SolidWorks Corporation since 2008. As you can see on the screen, we have 2 office locations. Our headquarters is in Montreal, Canada, and we have another office in Germany. Now let us talk a little bit about EMWorks products. We offer 4 products with various add-ons covering frequency range from DC to light. Our first product is called EMS, which will be the topic of today's webinar. This product is used for electric and magnetic field modeling for low frequency applications. It covers many applications like insulators, clutches, cables, bus bars, magnets, actuators, breakers, transformers, and electrical machines. Our second flagship product is called HFWorks, which is used for electromagnetic simulation of RF, microwave, high frequency and high speed electrical and electronic devices. It covers applications including wide range of antennas, resonators, filters, connectors, waveguides, etc. Our third product is called EMWorks 2D, which offers static analysis and covers simulation of planar and axisymmetric geometries. Our latest addition in the suite of electromagnetic simulation software is Motor Wizard product. This product is a template-based motor design software. It currently offers analytical and finite element analysis of brushless DC machines. In addition to these solutions, we offer few multiphysics add-ons like thermal, motion, linear statics, and circuits. In today's webinar, you will see few simulation results which has been achieved using 2 products, EMS 3D and EMWorks 2D. Now let us take a quick overview about EMWorks licensing structure. We offer 3 different programs: commercial, academic, and startup. Each program has its own benefits and requirements. Within commercial program, we offer perpetual licenses, while in the rest of the 2 programs, our licensing structure is usually annual based. The topic for today's presentation is simulating magnetic clutches. Arvind will use two products, EMS and EMWorks 2D, to address few challenges faced by an engineer while designing an electromagnetic clutch. These challenges may be to calculate a holding force or calculate forces at various separation distances and compute magnetic flux distribution. Before moving to the technical part of today's webinar, I would like to highlight few points. Kindly mute your microphones to avoid any background noise. You can use the GoToMeeting chat window to type in your questions, and we will answer them at the end of this presentation. A webinar recording will be sent to all the registrants in few days. Now, I would like to request my colleague Arvind to take over and present the next part of today's presentation. Thank you.
Thank you very much, Cal, and to all the participants who are here in today's webinar, welcome and thank you for being here. My name is Arvind and I will be handling this technical part of the presentation. As my colleague Cal mentioned and gave a brief introduction to what we will be seeing in this technical presentation, I just want to bring to your attention that if you have any questions, please feel free to use the chat window of the GoToMeeting to type in your questions. And at the end of this presentation, we will try our best to answer all of your questions. With that said, let us go ahead and start this presentation. Now, when you really think about an electromagnetic clutch, what today I'm going to focus on is to provide you with a workflow for you to conceptualize, design, simulate, and build your electromagnetic clutch. Electromagnetic clutches are quite simple devices, but we as engineers might tend to visualize them as an axisymmetric kind of model. Now, what I have is just a bunch of axisymmetric surfaces, but you have to imagine that if I were to revolve these things, I would actually get a clutch. Now, what are those axisymmetric components of a clutch? Now, certainly we have, as I highlight here, we have the coil that forms a very critical component of the clutch. Now, the coil is also surrounded by two steel components. Now, one is the core, other is the armature. So certainly the core is something that surrounds the coil and which acts as a conduit of the magnetic flux. And in the bottom here, you see what is called as the clutch plate, or we can call them armature, which actually experiences a force and it moves closer to the core and gets in contact with the core, and as a result, the clutch is engaged. Now, really, how does one proceed with from the concept to an engineering design of a clutch? Now, as a concept, there are probably several dimensions that come into play while designing this clutch. Now, I have lots of dimensions here, and certainly by no means this has been made to intimidate you. But some important dimensions that I do want to mention is really the gap distance between the armature and the core. Now that I've set it to 1.5 millimeters, and this clutch has these corresponding geometry, and this is something that I conceived as a designer, maybe in a piece of paper, and immediately I can translate those concepts into a sketch in SOLIDWORKS. Now, how do I know this clutch will work effectively? Now, for that to happen, I need to define certain design goals for my design. Now, one of the design goals that I have is obviously the outer dimensions are restricted to what I have here. Okay, so that has been properly designed with respect to the specifications from the application. So I have my clutch bounding box kind of defined. Now, the next goal that I have is I need to have a holding force of greater than 1.5 newtons. Now that is one of the design requirements that has been given to me by the team. So keep this in mind. I need to have a holding force of 1.5 newtons, and as my initial design starting point, I would like to find out what is the optimum gap that exists between the core and the clutch plate. Now that is the objective of my preliminary design. Now, right now I just have a concept in mind. I have a few design criteria that I need to meet. One of the most important design criteria here is that I need to get a force greater than 1.5 newtons. So let me find the optimal gap length that I need to start my clutch design so that I can get 1.5 newtons. Now, the program that allows you to do that in the EMWorks family is called EMWorks 2D. Now, what I have here is EMWorks 2D in action. Now, EMWorks 2D is an excellent product because it helps you to quickly simulate your designs either in a 2D axisymmetric fashion or in a 2D planar fashion. Obviously, only certain classes of problems will be amenable to be solved using EMWorks 2D, and the magnetic clutch that I have designed here happens to be one because it is axisymmetric in nature, about say this line. Okay, so that allows us to use EMWorks 2D to actually understand the initial design of this clutch. Now, EMWorks 2D employs parametric simulation whereby I can sweep through various values of this gap length to really find out what is the maximum value that I can start with so that the force is greater than 1.5 newtons. Now, to do a simulation in EMWorks 2D, the first step is to create a study. Notice here that I've already have a study created and it happens to be a parametric study. The next step is to define materials for my various components. EMWorks 2D comes with its own material library, which allows you to go ahead and define a material. For example, here I have an electric steel material, steel 1010, defined from the library, and you can see the magnetic properties, namely the BH curve of the steel shown here. Now, similarly, I have my other components that I have modeled. For example, this is the copper that you see here, that's made of copper. Then the armature is also made of steel 1010. So I have actually defined all the components, and I also have the air region that you see here outside, and it's very critical to model the air to understand the magnetic flux that could propagate through the air. Certainly through the gap here is air, and magnetic field is going to propagate through that region. Once the material has been defined, the next thing that we need to define is the coil. Now the coil definition is very simple. You select the cross-section face, okay, and that's the coil. And here when I go to the property, I can mention the wire gauge of the copper conductors that is used to wind the coil. Now I have a 19 wire gauge copper that is used to wind the coil, and the coil has about 345 turns in this cross-section area. So notice how I can actually input the real life coil definition in this particular dialog box. And I'm just going to start with an arbitrary current of 1 amp. So 145 amp turns as the current. Once the coil has been defined, next we go to request the program to find out the force acting on the armature. Now here is the force we have requested, the force acting on this particular face that is supposed to represent the clutch plate, and we are requesting the program to compute the force. I mentioned about parametrization. So EMWorks 2D and EMS 3D, which I will be showing to you just after this talk here, is going to have the option for you to parameterize your designs. What I mean by that is that you can actually keep any SolidWorks dimension or any input to the program as a parameter, and you have the ability to vary that parameter and do a sweep of that parameter to study how the parameter affects your results. In this case, how does the gap affect my force? Now here I have defined parameters and they are self-explanatory. I'm going to start with a starting gap of 1.5 millimeters, and I'm going to go every half a millimeter to go all the way to 4 millimeters. Now I have multiple gap values ranging from 1.5 millimeter to 4 millimeters. Okay. Now the objective is really to understand how the force varies as a function of the parameter. Now let me go straight into the results. There is one step of solving the problem which I had the luxury of doing before this webinar, so I will go straight to the results. Now the results give you how the force varies as a function of the gap length. So I'm going to just plot that, and here I notice how as the gap varies from 1.5 millimeters and increases all the way to 4 millimeters, the value of the holding force drops. And you see the drop in the force is not linear, but you can see the curvature for the drop in the force. Now, by looking at these values, I can get an idea of what that starting gap should be. Now, if you look at what the objective that I had at the beginning of the simulation, I mentioned that I would need a minimum holding force of 1.5 newtons. So I would like to start with a reasonable gap that ensures this holding force, and that comes at 2.5 millimeters. Now when I have a gap of 2.5 millimeters, I get a holding force greater than 1.5 newtons, in this case close to 1.8 newton, and so I cannot have a gap anything larger than 2.5 meters. Of course, I can have a gap much smaller than 2.5 meters to millimeters, and that leads to its own complexity in terms of actually assembling these components together and so on. So I would like to have as large as a gap as possible to start with, because the clutch also has other components like springs and so on that needs to be incorporated for the clutch to return back once I remove the excitation of the coil. So with all these constraints, I would like to keep the gap as high as possible, provided it meets the force value of 1.5. So as a result, let us understand that using this EM simulation, a very quick 2D simulation, I was able to come up with a minimum gap length that will be suitable for my design, and that happens to be 2.5 millimeters. Now there are obviously other things that one can view. This is the plot of the magnetic flux density that you see here, and you can see the value of the magnetic flux density and these red areas that tell you how this magnetic flux density, especially in the air gap, what are those values and where are exactly the areas inside your clutch where this flux density is high. Note that all we get is about 0.85 Tesla is the best maximum flux density that we get in the steel, and that is of no worry because it is much lesser than the saturation of the steel. Now another interesting plot that engineers would like to see is the flux lines. Now EMWorks 2D automatically gives you how the flux lines are distributed. Notice here the density of the flux lines kind of decide how much flux passes through that cross section, and this kind of plot is also extremely useful, and you can see how the flux jumps between the core and the armature, and you are able to see how the flux is well contained within the steel structure here, and there is very less flux and almost nil flux outside in the air region. Okay, now so let me recap. What we saw is we saw a very elegant workflow as a starting point for my magnetic clutch design. I can simply conceive an idea, draw the sketch, and do a simulation right inside SolidWorks to get forces, the flux distribution, and a starting point design for the minimum gap that I need to keep to ensure a force of greater than 1.5 newtons. Now, we all know that magnetic clutches are not as simple, especially the clutch plate. There might be perforations and holes and cutouts in the clutch plate. How do we deal with that? Realistic models are not as simple as what we saw here. So when you bring in some complexity to the design, EMWorks has what is known as EMS for SolidWorks that helps you to do that. So quickly, let me go ahead and let me bring a more realistic model of a clutch inside SolidWorks so that we can see how, when you have some models that are more realistic in nature than the clutch that we saw earlier, we will be able to simulate the same thing. Now, let me take a cross section of this model just to visualize everything that we did earlier. Now the coils remain the same, the outer diameter of the clutch armature is the same. You would have noticed all this. There is also a plastic bobbin around which the coil is wound. All of those come from the readily made sketch that we had previously. Okay, now the only difference is the clutch plate. Notice that the clutch plate is not a very simple a cylindrical structure, but it also has some cutouts and things of that sort. I mean, those are basically done to reduce the weight of the clutch plate and so on. So when you have a realistic clutch plate like this, then you are not, you are limited as far as your 2D simulation goes, okay? Because the problem needs to be completely axisymmetric, and because of these cutouts, the axisymmetry is violated. So the 2D result that we got earlier is just a good approximation. Nevertheless, it gave us a very good starting point for the minimum distance between the clutch plate and the core, okay, which happens to be 2.5 millimeters. Now let us see how we can use EMWorks 3D product by taking the same design and then simulating it. Now here I have EMWorks 3D. So if you look at the challenges as far as EMWorks 3D and why we transition to EMWorks 3D, just as a recap, we have realistic model of a clutch plate where axisymmetric approximation gives you only an approximate solution. We are interested in finding the exact force at 2.5 millimeters for this configuration of the clutch plate. Now for that, we use a program called EMS 3D for SolidWorks. Now, the look and feel of both the programs are very similar. Why? Because they come from the same company and they all operate inside SolidWorks, and they meet all the stringent principles required to be a gold certified partner of SolidWorks. Now, EMS 3D also has a very similar workflow, in namely create the study, define the materials. Now the same material library is shared between both the products. So whatever materials I defined in 2D, it comes through for 3D as well. The next thing I do is to define a coil, and notice that our definition of the coil, let me just take a cross-section view so that you can understand the coil a little better. Our definition of the coil remains the same as before. Here we select the components that comprise the coil. We also select the cross-sectional face. I can show a preview that tells you the direction of the current flowing through the coil. Okay, and then I can go to the coil definition. And if you have been following, I had a 19 gauge wire, copper wire with 345 turns. I put exactly the same coil in 3D as well. And I have 1 amps. So I have 345 amp turns as the total driving current. Okay. Now, once the coil has been defined, we also request the program to compute the realistic forces acting on the armature. Okay. Now, as before, EMWorks 2D, what you saw, EMS 3D is a finite element program, and the finite element program has a step called meshing, where I did not really take the time to show that in the 2D, but I will be happy to show you what the finite element mesh looks like in a 3D geometry. Notice how the EMS through 3D smart mesh puts a lot of elements on component of interest. Now we know that the clutch plate is the one that where we are interested in computing the force. So by having a very good mesh on the clutch plate, EMWorks EMS 3D ensures optimal mesh for a very accurate result. Now EMS 3D also has mesh controls and other things that we will not be covering in this webinar. Okay. Now, after all of this, we have run the simulation. So let us take a look at the results. You can also take a look at the magnetic flux density result that we saw in this 2D space. But now the results are a lot more concrete and appealing. Here I have a cross section of the magnetic flux density. So you see with the realistic model, you can see the magnetic flux density quite high in the middle, and you can see how the circulation happens throughout your model. Okay. The next thing that we are interested is to find out what is the armature force. Now the force acting on the armature is along the z-axis. You can notice here in the minus z-axis because the armature will be pulled towards the clutch. Now the force is little over 2 newtons. So that gives us a lot of relief that with a very let me say a first pass analysis in 2D, which gave us around 1.8 newtons, we were confident that 2.5 millimeter gap would be a good gap to start with. And we now model the realistic clutch plate on a more accurate 3D geometry. And now we are getting a result of over 2 newtons, which is a very big relief as a designer because it meets my threshold of getting over 1.5 newtons, which is really the attractive force with which the clutch plate is going to be held at this particular gap. Okay. Now with this force, I can go ahead and design springs and so on that will help you to for the clutch to operate. So this is the. In addition to this, I can get the resistance of the coil. So I'm using a coil with certain wire gauge material and number of turns. EMS also gives me automatically what is the resistance of this whole winding here. And one of the last things that people want to know is how hot does this whole core and the clutch coil and the clutch gets when it operates at this particular amp turns. Now to do that, EMS has a coupled thermal simulation. Now, the steps of the coupled thermal simulation is exactly the same as what we saw earlier, except that when you now define a study, you can couple EMS with a thermal solver. Now, EMS thermal solver can be coupled to magnetostatic or other kinds of simulations. In this case, we are coupling it to a magnetic simulation. And now, when you couple this to a thermal solver, in addition to the magnetic flux density, EMS will actually give you a temperature plot, a temperature profile. Now, here is a plot of the section plot of the temperature under which the clutch operates. So, under 345 amp turns, we see that the total rise in temperature above an ambient temperature of say 26 degrees centigrade is not much. The maximum temperature that we get is around 33.6. That is the temperature that we get in the coil, understandably so, because the coil is made of copper, it carries current, it has an I squared R heat going on, and that results in a temperature gain. And because the copper is in contact with the bobbin, which is made of nylon, which is a non-conductive material, you see how the temperature gradient happens, and you see overall the core of the clutch gets heated to somewhere around 31 degrees centigrade. So when you really think about it, the amount of temperature increase above the ambient temperature of 26 degrees centigrade is not much. So that also gives me a relief as a design engineer that my clutch is not going to heat based on the input current that we gave it. So as a recap, what I showed you today is a workflow for an engineer to conceptualize a design, to do that concept as a concept sketch in SolidWorks, immediately use EMWorks 2D to validate that concept and get some meaningful engineering solution out of it. Once the simulation was performed with EMWorks 2D, engineers can then move on to adding complexity to their model. In this case, we added a realistic armature profile, and then you have the companion product to EMWorks 2D, which is the EMS 3D product. The EMS 3D product can be used to study realistic geometries where we don't need any axisymmetric or planar symmetric kind of limitations. It allows you to study any geometry. And now in this particular clutch, we were able to find out the force acting for a particular gap of 2.5 millimeters. And we ensured that the force was well above 1.5 newtons. We also used the program to compute the magnetic flux distribution to see the areas where we have high flux. And finally, we computed the temperature distribution to see if the clutch indeed got heated or not. So apparently from the temperature values of just 33 degrees centigrade, we know that it is quite well within the safe operating temperatures. And now you can proceed with confidence for the further design of the clutch. For example, designing the springs, designing the casings, how to manufacture, and so on and so forth. So with that, I would like to end this technical portion of this webinar, and I would like to pass on the baton back to my colleague, Cal, who would complete the rest of the webinar. Thank you very much for your attention.
Thank you, Arvind. Thank you very much. Hello, everyone. Again, so my colleague Arvind utilized EMS 3D and EMWorks 2D products to show the complete workflow how to design an electromagnetic clutch. Now, let us take a quick overview on these two products, EMS 3D and EMWorks 2D. EMS 3D product offers electrical and magnetic solvers. In addition, few multiphysics options are available with this product, like thermal, motion, linear statics, and circuits. And this EMS 3D product is available in 4 package options: electric, magnetic, professional, and premium. The other product which Arvind utilized was EMWorks 2D. This product currently offers only static solvers, electrostatic, and magnetostatic. And this product can be accessed when EMS software is purchased. To get more information on this software packaging and pricing, you can connect with me after this webinar. Now, to design a electromagnetic clutch within EMS 3D product, magnetic bundle and thermal add-on can be utilized, and within EMWorks 2D product, magnetostatic solver can be used to design this electromagnetic clutch. As you see, this slide represents a very small subset of capabilities offered in our EMWorks products. And to design a magnetic clutch, 3 capabilities are highlighted and are utilized in the product demo you saw earlier. Number 1 is parameterization. So this capability enables a designer to run multiple what-if scenarios and to determine the best design. The second capability is thermal analysis, and through this multiphysics add-on, you can calculate temperature distribution in your model. And the third important feature we saw in the product demo today was axisymmetric modeling. This allows you to perform faster simulations and lets you analyze a portion of your geometry. Now let us do a quick recap on EMWorks products and their related applications. We can divide EMWorks offerings into two categories: applications related to low frequency simulation and applications related to high frequency simulation. Within low frequency category, we offer three products: EMS 3D, EMWorks 2D, and Motor Wizard. These products can be used to design and simulate applications like cables, insulators, clutches, bus bars, magnet arrays, actuators, eddy current braking systems, wireless charging devices, transformers, and electrical machines. And within high frequency category, we offer one product called HF Works. This product can be used to design and simulate high frequency applications like antennas, waveguides, connectors, resonators, and filters. Now coming to the learning resources we offer various free learning resources. With the software purchase or an evaluation license, users can access the demo viewer section of our software, through which they can access many predefined model examples and tutorials. In addition, we post application notes, blogs, and videos on our website and social media channels regularly. We also offer paid customized training sessions to all the users of EMWorks software. Anyone interested to get more information on our products, including a trial license, quotation, can go to our Contact Us page on EMWorks website, select the appropriate category, and submit your request. One of our representatives will reach out to you soon. Before we answer your questions, I would like to thank you all on behalf of EMWorks for participating in this webinar. Feel free to contact us after this webinar to get more information on our products. Thank you.